Let's add these up. Can you feel the excitement, the anticipation?
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's pentagonal number theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant. This guy and gang for inviting me.
Okay, so we've covered quite a lot of ground, and this is bringing us right to what this is all about, is this quadratic polynomial number theorem, whatever it is that I'm talking about there. Now, we just saw these recurrences where we did these things like this, where maybe I have this index, and I say this is P of n, and I'm going to do some kind of convolution or what have you with it, so that I knew where to start the next lines. As I would first go through and I would circle in my index the pentagonal numbers, you know, so that I knew when I had to make those changes. Think of the quadratic.
F of k equals 3k squared minus k over 2.
In terms of a sequence, because it's 1, 2,
5, 7, 12, 15, 22, 26.
dot, 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 dot. This whole infinite sequence is a quadratic. It actually is a more sensible way to think about a polynomial in terms of the sequence, because this is
F of k equals 3k squared minus k over 2.
And it's going to have, you know, it's going to have an a
ax squared plus bx plus c equals f of x.
form to it. So with these coefficients a, b, c. However, if I take any other point on this sequence and I say, well, that's my f0, all I'm doing is translating the index, and that's fine. But the thing I think maybe causes some misconceptions is the thought that because if I translate the index and I say that this is f of 0, I'm going to get different coefficients. And I could look at these and I could look at these and see no connection whatsoever. So every point on this sequence has a different set of coefficients that go with it. So people might think, well, there's an infinite number of quadratic polynomials because you get a unique one, you get a unique one for each entry, but you don't really. You're getting the same one. Any 3 values will determine a unique quadratic polynomial, whether those 3 values are interpreted as being coefficients, or if they're interpreted as being values of the sequence somewhere. It's all comes down to having enough equations to solve the however many unknowns you have. So if I designate 2, 0, 1, these 3 values as a value representation, and I define the value representation of a quadratic, but really of any degree polynomial as d plus 1 sequential numbers or what have you, you could say f of negative 3 equals this, and f of 22 equals this, and f of 1 equals this. And you could solve for the quadratic if you had the correct value and indexes. Any three values on this, even the real ones, probably even the complex ones. So for convenience, though, and to make it clear, we're going to have a standard definition of the three values for quadratic of f of negative 1, f of 0, f of 1. So I can do this and then generate my values. Just follow them, blah, 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 blah. Okay, so what would happen, for example, if we decided to start with 301 instead of 201 as our quadratic? Don't know what the coefficients are, don't really care. This is our quadratic, and we can figure out the sequence by taking differences. So we're adding negative 3 here, and then we're adding 1 here. Analogous to derivative, second derivative, and the second derivative will be a constant for a degree 2 polynomial. So that's 4. So we can add 4 again to get 5, add that to 1 to get 6. This is our sequence of our quadratic, and we want to do something similar to what we did before, only, well, let's just start with our index. K equals 0, 11. Let's go ahead and circle the values that are values of our quadratic. And 0, of course. And then we can ask, if we have a similar corresponding partition function, then we probably expect something along the lines of this P star of n equals the sum from k equals 1 to k, such that our f star of plus or minus k we want P star of k here. Then we want to follow this recurrence to generate it. So we start with, by definition, P of any P, any kind of partition of 0 is going to be 1. Let's just all accept that. Okay. And all negatives also equal to 0 as before. All right. So P star of 0 is 1. So if we take n equals 1 in this, then, well, this is going to be negative 1 squared, so it'll be positive, and this will be P star of n, which is 1, minus f of k, which is 1, and f of 1 is 1, so this is P star of 0, which we just showed, defined to be 1. So nothing's happening here yet. And so if we want P star of 2, then we let n equal 2 in this, and so we're going to get 1 plus the next one, which is 3, which is out of range. So it's just 1 again for P star of 2. To make this easier to see, yeah, we can do something like this.
Plus, plus, minus, minus.
So for 3, we have plus 1 gives us 2. For 4, we have plus 2 plus 1. So we have 3. For 5, we have plus 3 plus 1 is 4. For 6, we have 4 plus 2 is 6, minus 1 is 5. 7, we have 5, plus 3 is 8, minus 1 is 7. For 8, we have 7 plus 4 is 11, minus 1, 10. Yeah, let me realign these. Yes, P star of 9 is 15 minus 2 is 13, and then P star of 10, and again, because it's one of our circled values, have revealed another plus or minus sign here, and its value is 13 plus 7 is 20, minus 3 is 17, minus 1 is 16, and for 11, 16, 26, 22, 21. Okay, so this is our P star of K, and now let's use this as the partition sequence in deriving the expression for sigma of n. In other words, we're going to now look at sigma star of n. So all we're doing is just looking at the same thing, but with a different quadratic structure. Let's let this be the top matter. The first one is 1 multiplied by 1, so we're going to go 1, 1, 1. That's all we're doing is just copying like that. And then we're going to do 3, and now we've got, but remember we've got our factor in front here now on this version, so we have
3, 3, 3, 6, 9, 12, 15, 21, and 30. And then we're going to have negative 6, negative 6, negative 6, negative 12, negative 18, negative 24, and for 10, we're going to have negative 10, negative 10.
Let's add these up. Can you feel the excitement, the anticipation? Whatever it is, we're calling it sigma star of n. 1, 1, 4, 5,
6, 4, 8, 13, 25, 13, 34, let's go with 3, 24, 28, 7, 20, and, let's see, 6, 22.
12. Okay. To sort of quickly maybe intuit what these numbers might be related to the sum of divisors function, because it's not the sum of divisors normal. Can't be because of what we've done here. But let's do this. For each k, let's list the divisors of each of these numbers. So for 1, we have 1, and for 2, it's 1 and 2. And for 3, it's 1 and 3. And 4 is 1, 2, 4. The 6 is, what did I do? Yes, 5. That's what I did. This should be just 1 and 5.
So 6 is 1, 2, 3, 6. 7 is 1 and 7. 8 is 1, 2, 4, and 8. And 9 is 1, 3, and 9. And 10 is 1, 2, 5, and 10.
And 11 is 1 and 11. Okay. So we can see right off the bat we do have some legitimate sum of divisor values here. 11 plus 1 is 12. Something's wrong here. 16 minus 10 is 6. Yeah. Also for 9, we're getting a full sum. No. For 7, we're getting a full sum. For 5, we're getting the full sum. No. 3, we're getting the full sum. But not for 2. We're getting a full sum at 3, 5, 7, 3 squared, and 11. So let's do this, see if we can determine if these are a restricted partial, then what must they be? Our only choice here is that must be 1.
And for 4, to get 5, we just have a 1 and a 4.
And then for 6, to get 4, well, the only way we can do that is with a 3 and a 1. And then for 8, to get 13, well, it's 15 normally, so we're losing the 2. And the rest are being summed. 10, we only get 6, which can only be 1 and 5.
Now all we have to do is figure out what's the gizmo, what makes the difference. And it's pretty easy to discern. What we've got here is, well, first we're looking at 1 is always circled, 3 is always circled, 4 is always circled. So it's like once it's circled, it's always circled. So what's not circled? Well, 2, 6, 10, and what are all those? Those are the numbers that are equivalent to 2 mod 4. And that's it. So the others, the ones that are circled, we can observe then are the rest of them, aka all of those that are equivalent to 1 mod 4 or equivalent to 3 mod 4 or equivalent to 0 mod 4. Our value representation of the quadratic we used was 3, 0, 1. And the normal quadratic of the generalized pentagonal numbers is 2, 0, 1. What we find out is that this works for any beta 0 alpha where we're going to say that beta is greater than alpha. That's just a convenience. These are distinct numbers. So alpha is always the lowest. That's just so we don't flip the quadratic and we just get a duplication in the opposite direction. So, but they are always different. They're not equal. Those cases are excluded. We're going to look at that later. But so for now, it's either alpha. If alpha is 1, then beta can be 2 on up to the rest of the natural numbers, etc. If alpha is 2, beta can be 3 or more. If alpha is 4, like that. So we cover all of the positive combinations of a beta greater than an alpha in positive integers. And that what we then get is a sigma alpha beta function. And I write it like this: if it's clear, you could do alpha beta n, but I'm just going to go sigma alpha beta n because we're talking in general here. Is that this? So our sigma star is actually a sigma alpha beta, and what it is summing equals the sum of the divisors of n, divisors with the divisors also, such that d is equivalent to alpha, beta, or 0 mod alpha plus beta. And that is where the whole generalization I referred to in the title card comes from, and what it's all about. It is all about this alpha beta generalization of Euler's pentagonal number theorem. To all quadratics f of alpha beta of k equals alpha plus beta times k squared minus the quantity beta minus alpha times k all over 2. And we can see that when our quadratic is 2, 0, 1, we have 3k squared minus k over 2. So 2, 0, 1 is the Euler's pentagonal number theorem. Everything else where alpha is greater than 0 and beta is greater than alpha, and both of them are elements of the natural numbers, then that's what the generalization covers. This is what the generalization is over all of these alpha beta. And we're going to get analogous recurrences, identities, and restricted partition and sum of divisors functions. These restricted partition and sum of divisors functions are p alpha beta n counts partitions into parts equivalent to 0 mod alpha plus beta, or equivalent to alpha plus beta, or equivalent to beta mod alpha plus beta. And sigma alpha beta n sums, not counts, but sums divisors of n that meet these same criteria. Let's do something more exotic. Let's take the example 5, 0, 3. Let's see what happens. Here we got 0, 15. And so our P, 3, 5. So P, 3, 5 of 0 is going to be 1 by definition. And we know that our first values for the quadratic are 3 and 5. So there's no 1 to add, there's no n minus 1 to add, there's no, or k minus 1, n minus 1 to add, or n minus 2 to add. So these are actually going to be 0. And then when we get to here, we're going to add the n minus 3, n minus 1, 2, 3, which is the 1. So 4 is going to be 1, 2, 3, plus 4, 5, which is 0 and 0, so we get a 0 again. 5 is going to be 1, 2, 3, 4, 5, we get a 1. 6 is going to be 1, 2, 3, 4, 5, we get a 1. 7 is going to be 1, 2, 3, 4, 5, and that's going to be a 0. And by this point, we should probably expand our sequence here and make sure we know when the next circled number is coming up. So we're looking at adding -5 and then adding 3. So our difference is 8. So we go from -5 to 3, and then from 3 to 11. 11 plus 3 is 14. Plus 8 is 19. Plus 14 is 33. We're way out already. Yeah, and so in this direction we're adding a -3 and then adding a 5. So we're doing the same thing again with 8. So that's 5 plus 8, 13. That's going to be 18. And then we're going to be out of range. So our next one actually is 14. So we don't have to worry about anything beyond these first two up until that point. So we can just go ahead and 1, 2, 3, 4, 5 from 8. 1, 2, 3. Then 8 is 2. And 9 is 1. And 10 is 1. And 11 is 3. And 12 is 1. And 13 is 3. And 14 is 4. But we're circled here, so we know that we're going to land on a -1 when we get here. So 1, 2, 3, 4, 5. 4 minus 1 is 3, and then 1, 2, 3, 4, 5. That's 2. So that's our top reference matter. That's our P alpha beta. Okay, for alpha equals 3, beta equals 5. So now let's do our derivation of sigma alpha beta. And so to do that, we're going to copy this sequence, multiply it by the quadratic number, and list it out. And so this is plus 3 times this is 3.
0, 0, 3, 0, 3, 3, 0, 6, 3, 3, 9, 3. Do the same thing again for 5. 5, 0, 0, 5, 0, 5, 5, 0, 10, 5.
5. That's it. And then for 14, we're going to end up with -14, 0. And those are our sigma values. So let's start with from k equals 1 here. And we have sigma 3, 5. Okay, so 0, 0, 3,
0, 5, 3, 0, 8, 3, 5, 11, 3, 13.
and 0, 14, and 8. Alpha plus beta is 8, so we're mod 8. So the numbers that are equivalent to 3 mod 8 are going to be 3, 11, 19, etc. Numbers that are going to be equivalent to 5 mod 8 are 5, 13, 21, and numbers equivalent to 0 mod 8 are going to be 8, 16, 24, etc. All we really need to do is we can just list the divisor where it appears. So 3 has a divisor of 3.
And then so will 6, and 9, and 12.
And 15, and 5, 5, 10, and 15, and 8. And we would have 16 if we did it out here. Oh, now I gotta do it. 16 will be 1, 2, 3, and 5. 14 is here, 15 is here, 16 is here. Yes. So 6 minus 1 is 5. So we have 9 here. So this is 15. And for 14, it's going to be 0 again. So this is 24. So now we can do 11. We're going to have an 11 down here, and then, but no 22. We're not there yet. We'll have a 13. And then we'll have a 16. And there we go. That completes it. There's no other divisors of these things to write in here. So 3, 5, 3, 8, 3, 5, 11, 3, 13, 8, and 24. Bada bing, bada boom. I am grateful to the Summer of Math Exposition project and the idea of it, that here's a place where we can informally share mathematical teachings and information and research in a less formal environment without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on, and that's it. Thank you very much for watching my video.